Gas turbine engines are a relatively new invention. Functional gas turbine engines were put into operation at the end of World War II, about 1945. Progress has just exploded since then. And so now it's become part of a standard mechanical engineering thermodynamics class. Our thermodynamic model for a gas turbine engine is called the Brayton cycle. And it's just exciting to see the number of applications that the basic Brayton cycle has nowadays. And so I want to work you through what the thermodynamic cycle for the Brayton cycle, the model for a gas turbine engine, looks like, and give you hopefully a little background on it in the next video. So here is going to be what a basic land-based, or also known as stationary, gas turbine engine looks like. And so to point out, looks like we've got, you can see, let's see, how would we describe this thing first? Looks like an open system, doesn't it? Because we've got mass flowing into the inlet here. This is a compressor, an axial compressor that's taking in air and compressing it to a higher pressure. In here, this part two, this is the combustion chamber. And for our thermodynamic modeling, we're going to replace the combustion process with a high temperature heat addition process, Q dot H. So now this higher pressure, hot air is coming into our turbine, and where the turbine is producing power to do two things. It's got to drive the compressor, so you can see the shaft on this gas turbine engine. So it's a single shaft rotating, driving the compressor, but there's enough power left over for this stationary gas turbine to drive an electric generator. And so this is an example of a gas turbine engine that is a part of an electric power plant. Let's see. So I showed the air coming in. So here's going to be the exhaust gas going out from here. So open system, operating steadily. And so do you see, just from the picture you're looking at, this is different than an internal combustion engine that we just covered, where our thermodynamic model is for a closed system. Our model for this piece of equipment is going to be steady state, steady flow, open system, operating in a cycle, these multiple components. And so now here's going to be our thermodynamic model for our Brayton cycle. So remember, back of your mind, here's our schematic of any system operating in a cycle steadily in time. We've got a high temperature heat source. Well, that's going to correspond to this heat exchanger here. We've got Q dot N to the heat exchanger. This is our Q dot H. This black box is the equipment associated with the gas turbine engine, the compressor connected by a shaft with the turbine, and net output power coming out. Now, for our thermodynamic model, we realize that state 4 is basically exhaust gas, right? But for our thermodynamic model, to get back to state 1, to close it off as a cycle, we're going to say that we're rejecting heat to a lower temperature reservoir, or in other words, the surroundings temperature. But in general, we're not going to have to worry about analyzing this part of the process. Our big analysis for our gas turbine or Brayton cycle analysis is going to be analyzing the compressor, 1 to 2, analyzing the heat exchanger, 2 to 3, analyzing the turbine, 3 to 4. And what's that going to do? That's going to enable us to get the thermal efficiency of the power plant or of the gas turbine engine. Now, let's see. What I want to do, I've got to move my picture and do a comparison. Let's compare our air standard Brayton cycle thermodynamic model with our basic gas turbine engine. The compressor section, we're going to model both of these as adiabatic. So the gas turbine engine, that's pretty well an adiabatic process. The heat addition process, well, on the gas turbine engine, we've got a combustion chamber, but on our air standard Brayton cycle, our model is going to be constant pressure heat addition. And that's going to be a pretty good model. It's going to be a pretty good, accurate model. The turbine section, we're going to model as adiabatic. Now, for the ideal Brayton cycle, we've got adiabatic and reversible. For a real Brayton cycle or real gas turbine engine, it's going to be adiabatic and irreversible. And finally, the turbine exit, our model in the gas turbine engine is hot exhaust going to the surroundings. In our thermodynamic model for the Brayton cycle, we've got heat rejected to the surroundings in order to get our air standard air back into the inlet of the compressor. So it really makes a lot of sense. The way we're modeling our thermodynamic model, it makes a lot of sense, and it's a very good analogy to the real world. Well, what's that going to look like? What is our process? What is our Brayton cycle going to look like on a TS diagram? Well, probably in your class, you're going to start talking about the ideal Brayton cycle. What I'm going to try to do in this video is cover the ideal and the actual Brayton cycle all in one. Now, for an open system, so do you see that we have taken some steady state, steady flow control volumes, a compressor, steady state, steady flow, one inlet, one outlet. We've taken basically a heat exchanger. We're adding heat. Steady state, steady flow, one inlet, one outlet, and a turbine. Steady state, steady flow, one inlet, one outlet, and we're piecing them together to form up a thermodynamic cycle. And so when we do that, our best approach, similar to the power plant, is to draw a temperature entropy diagram. Now notice here there's no vapor dome. Why is that? It's because our working fluid air is an ideal gas. So we don't have a vapor dome for this TS diagram. If we did, it would be way down here. Okay, it's not going to show up on our TS diagram, but here we have two lines. See these two lines that should be kind of swooping up, but I'm showing them as diagonal lines. Those are two lines of constant pressure. This is going to be pressure 1. This would be ambient pressure, pressure of the surroundings. This constant pressure line is P2, a higher pressure, and that's going to be the outlet of the compressor. So do you see for the reversible and adiabatic compressor, we'd have process 1 to 2I, 2 isentropic. And you've already had some compressor problems to analyze, haven't you? You have in Chapter 6. And you also remember that, and so the isentropic compressor, the reversible adiabatic compressor, in the real world, there are irreversibilities associated with that adiabatic compressor. And so we draw our process line as a dashed line. It's irreversible, not quasi-equilibrium, up to state 2A. So 2A, state 2A is going into our heat exchanger, our heat addition model. So you see where I'm showing Q dot H going in to process 2 to 3. And it's going on steady state, steady flow at constant pressure. P2 equals P3. Okay, so that's modeling the combustion process for the gas turbine engine. Process 3 to 4. That's our expansion process for the turbine. If the turbine is ideal, in other words, if it's reversible and adiabatic, well, that's isentropic. So we'd have a vertical line, state 3 to 4I, for isentropic. But we realize that in the real world, that adiabatic turbine is going to have some irreversibilities in it, like unrestrained expansion, maybe some friction, okay, in the bearings. And so we draw a dashed line in from state 3 to 4A for actual to depict the actual adiabatic turbine. And then finally, we reject heat in our model. We reject heat to the surroundings to get back to state one. But I do want you to see, you might want to take a screenshot of this video or something like that. This is a pretty darn good TS diagram for our basic Brayton cycle with irreversibilities. Now here's our reminder of work that we've already done. Here's our schematic. We've got a system operating in a cycle. It's kind of a black box. Notice here our block arrows going clockwise there. It's showing that we've got W dot net power going out. It could be coming out of a shaft, okay, or it could be coming out in terms of a jet engine in terms of thrust. But for right now, let's say we're driving a shaft. Let's say we're driving an electric generator with our net rotating power coming out of that shaft, okay? Here is our high temperature heat added for the model of our combustion chamber. We've put together a compressor, a heat exchanger, and a turbine, all open systems, and we've got good experience at analyzing each of those for steady state, steady flow analysis. Okay. Also remember that we can calculate or we can determine the performance of our gas turbine engine, our Brayton cycle, from the thermal efficiency, and it's little W net divided by QH, the energy sought over the energy that costs. Remember, little w is W dot divided by M dot, and little q is Q dot divided by M dot. Another definition out of your book that is widely used in gas turbine engine performance analysis is called the back work ratio. So I'm just going to plop down this definition because some of your classes you're going to be asked to find the back work ratio, and it's simply defined as the negative value of actual compressor work. Remember, compressor work is going to be a negative number, isn't it? That's why I had to add that minus sign, divided by the actual turbine output work, W dot over M dot. So this is what the back work ratio is. W compressor actual divided by W turbine actual. Now, we've got an ideal gas here. This air is an ideal gas. Do you remember that enthalpy is a function of temperature only? I hope you do. And so, so do you see that if you can visualize the vertical distance from 1 to 2A as it's a visualization of work, okay? Enthalpy is proportional to temperature. And remember, so for an adiabatic turbine, the work, since Q is 0 for an adiabatic turbine or compressor, Q 0 minus W equals delta H. And so this vertical distance, these vertical distances are visualizations of work for an ideal gas on a TS diagram. And so notice here that when you're sort of studying this vertical line that I've shown in red is just a little bit taller than this vertical line. Okay. Thus, we have W net, and that is reflected in terms of the back work ratio. So what's the usual assignment for a Brayton cycle analysis, gas turbine cycle analysis? What are the typical assignments? Well, the typical assignments are to determine the cycle thermal efficiency and to determine the back work ratio of your engine. And so it looks easy, doesn't it? Wow. And I hope that you got so much practice that you say, yeah, this is really, it's pretty easy as long as you know the secret of analyzing each individual process. The thermal efficiency is, oh, darn it, look at that. I missed my dots. I should have W dot net divided by Q dot H. So I didn't put my dots down. But if I divide by M dot, I've got little W net divided by little QH. Okay, back work ratio we just defined as minus compressor actual work divided by W little w turbine actual work. You have to excuse me for not putting my dots there. It's a blunder. I'm going to remind you that when you read through your homework problems, you're going to be directed in your analysis to either use the air standard analysis, air standard. If all you see is air standard, that means use table A22 to look up your properties, enthalpy, PR, VR, and U. If you're directed to use a cold air standard, you're going to be going to A20 to get a constant value for CV and a constant value for K, which was CP over CV. Get more guidance from your instructor on this, but you're going to be using one or the other categories of analysis, ideal gas analysis, when you're going through your performance analysis of the gas turbine engine. So let's see if I can walk you through a representative Brayton cycle analysis example problem. And this would be like for a real gas turbine engine where you're given a lot of real world data. Okay, so it says a stationary gas turbine, so we're running a generator. Stationary gas turbine engine operates on the traditional Brayton cycle with irreversibilities in the compressor and turbine. The inlet conditions to the adiabatic compressor section are 100 kPa and 290 degrees K. So that's about ambient conditions. The compressor pressure ratio is 32. In other words, P2 is 32 times bigger than P1. The turbine section inlet temperature in the cycle is 1300 K. In other words, we have added fuel and air in the combustion chamber, and the resulting high temperature air or exhaust gas has reached 1300 degrees K. That's really hot. Also given is compressor efficiency is 85% and turbine efficiency is 87%. And the traditional question is determine the engine's thermal efficiency and the back work ratio. And so you say, well, how would you do that? Well, it could be that you say, well, gosh, I need to start looking for formulas in the book. Now that's going to be tough because this would be an example problem of a real gas turbine engine, not an ideal, because you're given compressor and turbine efficiencies that are less than 100%. So you're not going to find formulas in the book for this analysis. And the chances are mighty good that you're going to have a problem like this, certainly in homework and maybe in a quiz or a test. So I want to encourage you to understand, how do you analyze this engineering situation, process after process after process, instead of seeking formulas in the textbook? Well, we're going to start with a sketch. Now, one thing in the given information was that m dot was not given. M dot is unknown, okay? But you're asked to find the thermal efficiency and the back work ratio, and you're going to be able to do that even without knowing what m dot is. So remember, you're going to be looking for little w net, kilojoules per kilogram. You're going to be looking for little qh, kilojoules per kilogram, okay? And you're going to be able to do it. You've got some experience doing that, okay? Here's what our sketch looks like. So we're going to draw out two things. One is we're going to draw a sketch of our equipment and label states 1, 2, 3, and 4. Compressor process, adiabatic compressor, 1 to 2. Constant pressure heat addition, 2 to 3. Adiabatic turbine process, 3 to 4. Do you see a shaft coming out of the heat exchanger? Is the heat exchanger lifting a weight? No. So that tells me that there's no power or work associated with the heat exchanger process 2 to 3. Do you see that there's a single shaft coupling the turbine and the compressor? So the turbine is going to put out an amount of work required to drive the compressor, and it's going to put out more work so that we can pull what's left over to, let's say, run an electric generator, little w net. Okay, and so here is our TS diagram. That's another very important part of our problem-solving process, is to draw the TS diagram. 1 to 2, that's the compressor process. 2 to 3, that's the heat addition process. 3 to 4, that's the adiabatic turbine process. And it's my hope that you fully understand why I've got a solid line and a dashed line depicting both the compressor process and the turbine process. So this is not brand new material. In Chapter 6, you've been through, and also in Chapter 8 with steam turbines, this idea of a reversible adiabatic process and then an adiabatic but irreversible process. Let's plan ahead. Okay, let's plan ahead with things we know. We've got open systems. We've got 3 open systems to analyze: steady state, steady flow, 1 inlet, and 1 outlet. We've got an ideal gas relationship, P times little v equals RT. We may use that, okay? And we've got the first law. And look, if I divide everything by m dot, I've got little q in minus little w out equals h out minus h in. And that applies to all 3 of the processes we're going to analyze, doesn't it? Well, let's tabulate what we expect to get for process 1 to 2. Q dot in, 0, adiabatic. W dot out, compressor process. I can expect to get a negative number there. Process 2 to 3. Q dot H, we need to find that because that goes into our thermal efficiency denominator. W dot out for the heat exchanger. Well, that's 0, not lifting a weight. 3 to 4, okay. Heat transfer, none. It's an adiabatic turbine, okay. W dot out, positive, okay. We're getting positive work, W dot over M dot, from the turbine. And if we add up all of these, that's going to give us W dot net. That's going to be the numerator for our thermal efficiency. So, and it turns out we don't even have to worry about this process 4 to 1. Don't even have to worry about it. We're not focused on, we don't need anything from analyzing that process. Okay, so I think you see where we're headed. We're going to start at the compressor, move to the heat exchanger process, 2 to 3. We're going to analyze the turbine process, and then we'll put it all together to get the thermal efficiency. Let's start at the inlet of the compressor. Traditionally, for gas turbine engine analysis, we start at the inlet of the compressor because P1 and T1 are typically given. P2 is known. Remember, the pressure ratio was given, so P2 is a known value. T3 is given, the outlet temperature of the heat addition process. T3 is given. W dot net power, we need to determine that. I shouldn't have put that. That's not given. Okay. So let's run through the solution. The first thing we're going to do is study the isentropic process 1 to 2I for the compressor. That's going to enable us to determine T2I and the work out isentropic. But we don't have an isentropic compressor, do we? We've got an adiabatic but irreversible compressor. But once we've got W out isentropic, we can apply compressor efficiency to determine W out actual. That's good. We need that. All right. Then we're going to use the first law to determine T2 actual. We're going to need an H2 actual because we're going to need H2. Think ahead about the first law. And you see that our next step is to analyze the heat exchanger. So that's why we're going to need to find T2 actual and H2 actual. We're looking ahead now. So the next thing we do is we need to analyze the heat exchanger process 2 to 3 to get little QH, little Q added, okay? we'll use the first law. Let's see. Q from 2 to 3 minus W from 2 to 3, well, that's 0, equals H3 minus H2. Well, okay, let's say we just found H2 actual, H3. Well, we can look that up in table A22 because we're given T3. Great, so we're in pretty good shape. The next thing we're going to do is analyze the turbine. Well, first thing we're going to do is analyze the isentropic turbine, 3 to 4i, to get a couple of things. We're going to get T2 isentropic, and that's going to enable us to get W out. And look at that typo. That should be W out 3 to 4 isentropic. There's a big typo there, okay? 3 to 4, okay. So, well, we've determined the isentropic output of the turbine, but wait a minute. We don't have a reversible adiabatic turbine. We've got a adiabatic but irreversible turbine. We'll use our definition of turbine efficiency. We're going to get a lower number, aren't we, to find W out 3 to 4 actual. So at least I corrected my typo here, and I need to fix that typo there. W out 3 to 4 isentropic. Wow, okay, and so let's see. That simple as that. So we have everything we need to determine the thermal efficiency and the back work ratio because we got the two work actuals. We got W actual for the compressor. It's going to be a negative number. We got W actual for the turbine. And we got QH in the high temperature heat addition process 2 to 3. Boom. Looks easy, doesn't it? The devil's in the details. But really, I find this a little easier to do than the internal combustion engine models. Let's look at some details for the isentropic compressor process 1 to 2i. So here's my little sketch down here in the bottom left, so you'll remember what we're looking at. We may be directed to use the cold air standard, or we may be directed to use the air standard. Let's say we're directed to use the air standard, okay? Because that's going to probably be most common in your class, okay? Here is my TS diagram. I'm looking at the isentropic process first, 1 to 2i. Okay. Let's say we've got the air standard analysis. We're using table A22. We've got variable specific heat. P2 over P1 was given. It was a given number. We'll look up PR1 because we have T1 in table A22. We plop down a number. For an isentropic compression process, any isentropic process, P2 over P1 equals PR2 over PR1. So we'll solve for PR2. Well, if we've got PR2, we go right back to table A22 and we back calculate T2 isentropic and H2 isentropic. So we're going to need that we're going to use the first law to determine the work. That's why we need to do that. Okay, so let's find the work done. Okay, so for the let's stick with the air standard cycle. So do you see that once you've got H2i, you can apply the first law. First law for 1 to 2 isentropic. Q from 1 to 2 isentropic. That's 0. Okay, adiabatic minus 1 to 2i. Work 1 to 2i. That's what we're looking for. It's simply going to be H2i minus H1. Okay, not bad. So there's two different ways you can do it. If you're assigned the cold air standard, you might take a screenshot of this screen so you can easily see how to calculate H1 minus H2i. It's Cp times delta T. Air standard, it's a matter of looking up and interpolating for H2i. We got the compressor, okay. The next thing we've got the work of the compressor isentropic, but we don't have an isentropic compressor. We've got a real compressor, so we're looking for the actual work, W12A. And I remember from chapter 6 work that I would expect the actual work to be more negative for a compressor than the isentropic work, W dot over M dot. And so very quickly I can plop down W from 1 to 2 actual is W1 to 2 isentropic divided by the compressor efficiency. Well, great. I'm going to calculate that. And then looking ahead, I'm going to need H2 actual to do my first law analysis on the heat addition process 2 to 3. So I'd better get it. So H2 actual using the first law is Q minus W equals H2 actual minus H1. Solve for H2 actual. And of course, it's going to be a number that's bigger than H1 as a check. Okay, so you've got H2 actual. On to the heat addition process. 2A to actual to 3. Okay, so let's say we're doing the air standard analysis. We've got 2A. We're given T3, so all we have to do is go to table A22 to look up H3. We'll apply the first law, Qn from 2A to 3 minus W, that's 0, equals H3 minus H2A. Boom, got it. We've got a number for the heat added, just like that. Okay, we're coming down the home stretch. Well, the next thing to do is study the isentropic turbine process, 3 to 4I. Well, we know we don't have an isentropic turbine, but if we can get some information about the isentropic turbine, we'll use our knowledge of turbine efficiency to get the actual work. Let's say we've got air standard. Okay, well, so many students overlook the fact that notice here on our TS diagram that P3 equals P2 and P4 equals P1. And you were given P2 over P1. And so do you see that P3 over P4 exactly equals P2 over P1? Okay. And so that's basically given. And so the same, the nice isentropic relationship, P4 over P3 equals PR4 over PR3. P4 over P3 is going to be some number. PR3, well, you have the temperature T3. You can look up PR3, table A22, solve for PR4. Okay, I've got a number for PR4. Well, if you've got PR4, you can interpolate back for T4 isentropic, T4I, as well as H4 isentropic. Write those two numbers down. Okay, so now we're going to apply the first law to our adiabatic turbine. Here it is, Q from 3 to 4, turbine process, 0, adiabatic, minus the work from 3 to 4 isentropic. It's H4I minus H3. We now have both of those numbers. So the work from 3 to 4I is simply H3 minus H4I. We've got a number for the isentropic work of the turbine. Wait a minute. I've got an actual turbine. I've got the turbine efficiency. I can solve for the W 3 to 4 actual. And here it is. Let's see. We use our common sense. Would I expect to get more power out of an actual turbine than I would an isentropic turbine? No. I'd expect to get less power because of unrestrained expansion. So without going back to a formula sheet, I can write that the work from 3 to 4 actual is going to be the turbine efficiency times the isentropic work. So now I've got a number for work from 3 to 4 actual. Yeah, cool. Now, when I think about what am I looking for, I'm looking for thermal efficiency and backwork ratio. I don't even have to go through that effort of finding T4I and T4A because it's not needed. So actually, this is sort of nearly the end of my work. Thank goodness. Sure enough. So look, let's see. W net, the numerator of thermal efficiency. It's simply the sum of the two work terms. Well, the work from 1 to 2 actual is less than 0. the work from 3 to 4 actual is greater than 0. So I'm going to get some number for that. Net work, QH, well, that's simply Q from 2 to 3, 2A to 3, and boom, I've got the thermal efficiency. And darn it, look, another typo. That's not compressor efficiency. That's the thermal efficiency of the cycle. Shame on me for not detecting that terrible copy and paste practice. Thermal efficiency, not compressor efficiency. Shame on me. Okay. Back work ratio, I have to refresh my memory on that. That's going to be minus work of the compressor actual. Well, it's minus that number divided by work of the turbine actual, that number, W 3 to 4 actual. And I'm done. I've got it. I'm so embarrassed that that should be thermal efficiency, eta TH, not eta compressor. Shame on me for that. Now, I didn't go through any numbers, any numerical work, did I? If you're interested in, let's say you need a memory refresher on turbine efficiency calculations or compressor efficiency calculations, you can go to my playlist, which is example problems for open systems, and get a refresher course on both of those. Or if you're interested in a couple of fully worked out Brayton cycle, gas turbine engine, Brayton cycle analyses, go to Homework Solutions. I have fully worked out problem 938, and I believe I've worked it out both for the air standard analysis and the cold air standard analysis, and I believe I compared that. I'm not sure, but you might take a look at problem 938, fully worked out with numbers. And in the same way, I've got another example of a gas turbine engine that's driving actually a high-speed destroyer called Brayton Calcs in my playlist called Example Problems, Air Standard Cycles. So I have a playlist that's devoted to air standard cycles. So Brayton Calcs is another worked out problem if you're interested in seeing the nitty-gritty numbers associated with these problems. So we've gotten to the recap of our gas turbine engines Brayton cycle. So recognize here that the Brayton cycle is dramatically different than our models for internal combustion engines. So the Brayton cycle involves components that are open systems, steady state, steady flow. Okay. Thus, we're dealing with enthalpies, H, instead of U. And so many students overlook that very important fact. Okay. We've got adiabatic and irreversible compression and expansion in the compressor and turbine sections. For this example I used, the constant pressure heat addition models the combustion chamber process of a real gas turbine engines. And when you run through the numbers, you're going to see that there's the back work ratio is very high compared to a steam plant. And the reason is because you're dealing with an ideal gas. Remember, for a steam plant, you're expanding superheated vapor that's behaving like a gas, but you're pumping a liquid. So for a steam power plant, the back work ratio is much better than the gas turbine engine. So now I may have misspoken. The back work ratio is dramatically different, and so for the steam power plant, I would expect a low number for a back work ratio, and for the for the gas turbine engine, a high back work ratio. Yeah, I think I'm right. I was self-doubting myself, but I think I'm correct. High back work ratio compared to the steam power plant, which has a low back work ratio. Well, I thought my eyes were going to pop out when I saw that compressor efficiency instead of thermal efficiency. It's a terrible typo blunder. Please excuse it, but we're going to have to just let that slide and go through. As long as you pick out that the thermal efficiency is the energy sought over the energy that costs for all of our cycles. I hope that helps, and I hope that you might give some of those numerical worked out gas turbine analysis problems to get you started on analyzing your own situations.